Hello everyone, welcome to this video. This time we are going to be doing another example. This example was once again taken from Griffiths' Introduction to Quantum Mechanics book. These are the problems 2.8 and 2.9. I made a little addition, so it's not exactly as they appear in the book. What I did is I just took the parts of these questions that are about the topics that I wanted to talk about, which is basically finding this wave function given a certain initial wave function. So that's what we want to do. So I took the parts of these problems that would be interesting for this. Okay, so this problem tells us that there's a particle in the infinite square well with this initial wave function. We have to first normalize it, then we have to graph it, just a sketch to see, which stationary state it most closely resembles. That's part A. Then we want to find the wave function as a function of time. We only know what it looks like at the beginning. We don't know what happens later. And then we want to evaluate the first three coefficients numerically and then comment on the meaning of those numbers. Okay, so in order to normalize, I hope by this point you all know this well. We just do this product between the conjugate wave function and the normal wave function. In this case, it goes from 0 to a. It's a real function, so it's just going to be the function squared, a minus x squared dx. So let us just now do this quickly. We can take this big a squared outside, get ax squared times a squared minus 2ax plus x squared dx. And now we just do this product so that we can just integrate each term separately. This is just a quite basic integral, so I'm not going to comment too much. If there are some questions, I do recommend going back to the basics of integration. So I'm just going to speedrun this a little bit. And well, now we just integrate each term separately. And we are going to get in this first term, it's going to be a squared x cubed divided by 3 minus 2a x to the 4th divided by 4 plus x to the 5th divided by 5, and all this evaluated between 0 and a. And now we just replace the limits. The one with 0 will just be 0, so we only get these with a, so we get all these are going to be to the 5th power divided by 5, and now I have to take the common denominator. So in order to find it, the easiest thing in this case is just to multiply all of these, 3 times 4 times 5, which is 60, and then we just see how much we need to multiply to each of these terms in order to get to 60. This is just normal algebra, so I'm just going to do this quickly. We get 20a to the 5th minus 15 times 2 is 30a to the 5th plus 12a to the 5th. And well, here we just sum these. We get 32 minus 30, so we get 2 divided by 60, so we get just a squared times a to the 5th divided by 30. And this has to be equal to 1. Remember, we are normalizing. So from there we can find that a squared is 30 divided by a to the 5th. Or if we take the square root, we see that the normalization constant is just the square root of 30 divided by a to the 5th. So that is the normalization constant that we were looking for. Now, the next step is to graph this function. So let us do that. So just a quick sketch. We want to know what this looks like. So this formula right here, we can rewrite it, there we go, as a times xa minus x squared. I just did it to show that this is a parabola, upside down parabola, so it's going to cross the y-axis, the x-axis at the points 0, 0, and a. And its maximum is going to be at the average of these two. Remember, its x-coordinate is just going to be the average of its two zeros, so it's going to be at a divided by 2. So it's just going to be something like this. But we don't really have to go into too much detail. So we can see that this really looks like the first stationary state. Remember that these stationary states are even and odd interchangeably with respect to the center of the well as n goes up. And the first one looks something pretty similar to this. It's a sine function. It's not a parabola, but it's a sine function, and it is quite similar. So that is part A. It's quite simple. That's why I wanted to do it somewhat quicker, because part B is going to be a lot trickier. Maybe not like all that much trickier, but it is going to be somewhat annoying. So let's get to it right away. So we want to find these coefficients. So remember, we have this initial wave function, and we know that this wave function can be written as a linear combination of the solutions to the Schrödinger equation that we have already seen. Right? The square root of 2 over a sine of n pi over x over a times x. So here we can apply Fourier's trick. We did that in a previous video, and we can see that these cn's or cm's, it doesn't really matter what you call them, this is just going to be the integral over psi n of x psi x comma 0. I'm going to write this out just to make sure this is the big psi, right? dx. So this is what we will have to do. We need to compute this integral so that we can then put this into our equation for x comma t, which is just going to be in the of this cn times this psi x comma 0 times, oops, sorry, this is just our psi n of x times e to the minus I e n t over h bar. There we go. So this is our goal. We have to find these coefficients because we already know this. We know this. I mean, the energy, we already know what it is for this infinite square well. So the whole issue here is just to find these constants Cn. So that's what we have to do. And in order to find it, we need this formula that once again we derived in a previous video. So if you do not understand where it comes from, then you should really go rewatch that. I have a playlist with all the videos on quantum mechanics, so you will find that easily. Okay, so let's now do this. So Cn is just going to be the integral from 0 to a of the square root of 2 over a sine of n pi over a x times now the wave function from this problem, which is just the constant a, times, I believe it was, I'm gonna double check, yeah, it was, wait, what? Okay, there we go. X, a minus x. I'm gonna triple check, a minus x, yes, okay. Dx, yes, okay. So now we have to do this integral, so let's just multiply this factor here, so we get integral from 0 to a square root of 2 over a times big A. And actually I'm just going to pull them out of the integral. We don't really need to keep them in there. 0 to a times the sine of n pi x divided by a times a x minus x squared times sine of n pi x divided by a dx. Okay, so I just multiplied this here. So we're going to get two integrals that we need to solve. I'm going to copy this, go to the next page. Okay, so let's now call this part right here without the a. I'm just going to, that right there is going to be I1, and this whole thing is going to be I2. So let's solve them separately. For I1, we are going to have to do integration by parts. You might see where this is going to be going, but as I said previously, I'm just going to do these integrals just to make sure that everyone here knows how they are done. So this is going to be u will be x, du will be dx, dv will be sine of n pi x over a dx, and v will then be, well, the integral of this, which is just minus cosine n pi x over a times a over n pi. So, well, now integral number 1 we have to now multiply, so we get minus a divided by n pi times x cosine of n pi x divided by a. And then the second term is going to be minus the integral of the product of dx and this thing over here, but this already has a minus sign, so it's going to be plus integral from 0 to a. Oh, this is evaluated between 0 and a divided by n pi cosine of n pi x divided by a dx. Okay, great. So now let's continue. Now we just evaluate in this first part these limits, so we get minus a squared divided by n pi cosine of n pi. These a's will cancel out, and the second term is just 0 because there's an x here that will be 0, so that whole thing is just 0. And this integral right here will be a divided by n pi squared, because we have to integrate this, and this is just the sine of n pi x divided by a, and there comes this amount a over n pi because of the chain rule, as we have already done many times, and this is between 0 and a. But as we saw before, this is just going to be 0. Okay, so this part is just 0. So this I1 is just going to be minus a squared divided by n pi times the cosine of n pi. But what is the cosine of n pi? If n is 1, it's going to be cosine of pi, which is minus 1. If n is 2, it's going to be 2 pi, which is 1. And if it's 3, it's going to be minus 1. And if it's 4, it's going to be 1. So it's going to be going from minus 1 to 1. So the way we can write that is to say minus 1 to the n. So if n is 1, it's going to be minus 1. If n is 2, it's going to be 1, and so on. So that matches cosine of n pi, so we can just rewrite it in that form, which is much better. So that is our first integral. So our second integral is going to be, I'm going to leave the minus sign outside. Our second integral is just going to be the integral from 0 to a of x squared sine of n pi x divided by a dx. I really have to make sure that I don't forget to put that minus sign in there when I replace it. Now, that's normally the difficulty in these problems. They are a lot of algebra, a lot of integration, so make sure that you don't leave something out. Okay, so this second integral we can now solve by doing integration by parts twice. So let's first call u x squared, so the u is just 2x dx. And well, I think my camera is going to block this if I continue writing there, so I'm going to move it over here. So dv is now going to be sine of n pi x over a dx, and v is going to be minus cosine n pi a over x times a divided by n pi. So now this integral is just going to be, we multiply this first term, minus x squared a divided by n pi cosine of n pi over ax minus this other integral, but there's already a minus sign, so it is now positive, and we get 2x cosine of n pi x divided by a, and there's also this a divided by n pi dx. Okay, so here we have to once again apply integration by parts, so we call this integral just I3 without the constants. We're going to leave them outside. So for I3 we call u is just going to be x, du is going to be dx, dv is going to be cosine of n pi x over a dx, and v is just going to be sine n pi x over a divided by n pi. So I3 is going to be x sine of n pi x divided by a divided by n pi times a, and this between 0 and a. But this is going to be 0, as we have seen many times already, right? Sine of n pi is 0, sine of 0 is 0, so both terms will just be 0. So we are left with the second one, which is just minus the integral of from 0 to a of a divided by n pi sine of n pi x over a dx. So when we do this integration, the integral of sine is minus cosine, so this minus is just going to be a plus now, and we're going to get another one of these, a divided by n pi, so we get a divided by n pi squared times cosine of n pi x divided by a, evaluated between 0 and a. Okay, so now we have to simplify this a little bit, so let's take it to the next page. So I3 is going to be this right here. So let us evaluate it. When we evaluate it at a, we get, well, this same constant is going to be here in front, and cosine is just going to be cosine of n pi minus cosine of 0, which is just 1. But what is cosine of n pi? We already saw this before. This is just going to be minus 1 to the nth power. So now we found I3. Let us now replace it in our expression for the second integral. Let's see, it was right here. So I'm going to copy it. There we go. Okay, is that a minus sign, or did I take it from? Okay, it is a minus sign. Okay. Wait, did I not evaluate this term right here? Okay, this term is supposed to be evaluated between 0 and a. Okay, I have to do that now. Okay, and this integral, we already know it. We have to not forget about this 2a divided by n pi. Remember, we didn't take that into consideration when we defined I3. So our result for this, which is right here, is now 2 times a divided by n pi cubed, because we had to multiply it by these constants that we had outside of the integral, times minus 1 to the nth power minus 1. Okay, and then we have this right here, which we have to evaluate. So when we evaluate it at a, we get minus a cubed divided by n pi cosine of n pi. And when we evaluate it at 0, it's going to be 0 because of this x squared right here, which is just going to be 0. So then we have this other term, which is just 2a divided by n pi cubed minus 1 to the nth power minus 1. There we go. So now we can factor out this a cubed, but we don't really have to be factoring out that thing. What we have to do though is this cosine of n pi is just minus 1 to the nth power. So this is our second integral, which we now have to put into the expression for Cn, right? We have this expression for Cn, which is, let me look for it, right here. So we have this first integral that we already solved. So Cn was just square root of 2 over a times big A, and then we had these two integrals. Wait, where is it? There it is. Yeah. So the first integral, we did not take this a into consideration, so we have to multiply it by a. And this is the result right here. So we get minus a cubed minus small a cubed times minus 1 to the n divided by n pi. That is from I1. Just gonna double check. Yes, that's it. And now we put in the result from I3, which is right here. Was there a minus sign between these? I just want to double check that. Yes, there is a minus sign right here, which we also did not consider when we defined I2. So we have to put it here now. So we get minus what we had here. So we have minus a cubed divided by n pi minus 1 to the nth power minus 2a divided by n pi cubed times minus 1 to the nth power minus 1. Okay, so this minus minus is just going to be a plus. It's going to be positive now. There we go. So what we can see here is that these two terms are just going to cancel each other. So that's nice. And we can also write in now the value that we found for this big A. I didn't do it before because there was not really much point to it. I was just going to have to write extra. So now we can write it in. It was 30 divided by a to the 5th. And what we have in these parentheses is just going to be this thing right here. We can put this minus sign into the parentheses here. So we just get a cubed divided by n pi. Well, all of this is cubed. And there's a 2 multiplying here. And now we have 1 minus 1 to the n, right? And that is because we put the minus sign into this. Okay, we're doing great. So now what we want to do is just continue to simplify this. So we can now multiply this. We can write 30 as 2 times 15. So we can take a 2 outside of this square root. We get 2 times square root of 15. And down here we get a to the 6th power inside the square root. So we can just write it as a cubed. And there's also an a cubed right here multiplying. And there's also a 2, and there's also this n pi cubed and 1 minus 1 to the nth power. So we can just cancel this with this. We can put this 2 and 2 together. So what we get now in the end is we got that these coefficients are 4 times the square root of 15 divided by n pi cubed times 1 minus 1 to the n. Okay, so these are the coefficients that we were looking for. It may not be the prettiest expression, but we can actually get something much better if we see what happens if n is even and if n is odd, because n, what it's basically doing here is that it's telling you whether this is going to be minus 1 or 1. So let us see what happens for even values for n. We get that Cn even. This is just going to be 4 divided by the square root of 15 divided by n pi cubed. And here we get 1 minus, but now we get minus 1 to the 2nd power or 4th or whatever. So this is just going to be 1. So this is just going to be 0. So when n is even, Cn is 0. And when it is odd, we get the same thing here, n pi cubed, but now we get 1 minus 1, which is just going to be 2. So we get 8 times the square root of 15 divided by n pi cubed. Okay, so this is our expression for our Cn's, which is, as we can see, is only valid, is only non-zero whenever n is odd. So with this in mind, we can now finally, and this was the point of this whole thing, as we said in the beginning, we can now find our psi of x and t, which is just going to be a linear combination from n equals 1 to infinity, and only considering the odd terms. I mean, you could consider all n's, but you know, all even ones are going to be 0, so it doesn't really make sense to include them, but doesn't change much, it's just 0. So our Cn's are 8 square root of 15 divided by n pi cubed, and this has to be now multiplied by our square root of 2 over a sine of n pi x divided by a. Now, since this was a long calculation, I just want to make sure that it's all right. And it is up to a little detail. Of course, I almost forgot about it. Good that I checked. we now want to include this time dependence. So this is minus I en t divided by h bar. Now we can do a few simplifications here. So we can take all of these things that do not depend on n, we can just take them outside. So we get 8 square root of 30 divided by pi cubed square root of a. You could also write this 8 as 2 cubed and put it together with a pi, but it's the same, doesn't really matter. The sum of n odd of 1 over n cubed times sine of n pi x over a e to the minus I. And now what are our allowed energies? Remember, it's just n squared pi squared h bar squared, but it cancels out with this one, so it's just h bar times t. Well, it looks a little bit separated, so let's just write it all together. There it is. Okay, and this has to be now divided by, whoops, there we go, by 2ma squared. So this is the result that we were looking for. This is our wave function. So this was the whole point of having this a complete set of functions, because we can now find our solutions, which had this 1 over n cubed. These are our coefficients. So let us now evaluate our coefficients. So C1, let me pull up my calculator. This is just going to be 8 times the square root of 15 divided by pi cubed. So if I put it into the calculator, this is going to be approximately 8 times square root of 15 divided by pi cubed. This is going to be 0.99928 basically. So it's quite close to 1, and C2 is obviously going to be 0 because it's even. So C3 is now going to be 8 divided by 15 divided by n cubed. So n is now 3, so it's going to be 27 pi cubed. So this is basically the result that we got from C1 divided by 27. And this is going to be approximately, this is going to be 0.03701. Okay, so what we can see here, wait, did I do this correct? 0. Yeah. Okay, yeah, it is correct. So because these C1s are proportional to the probability of each state, we can see that this state is going to be dominated by the first state. So this is a linear combination of all of the possible states, but the state that is going to be the most in, so I mean this function is going to be the most in this first state. That is what this C1 tells us, right? Because as we said in our previous video, the sum of all of these things squared has to be equal to 1, right? These are just going to be the probabilities. So the probability of finding our particle in the first state will be 0.99928 squared, which is basically 0.9986. And the probability of finding it in the second state would be 0.03701 squared, which is very small, 1.34 times 10 to the minus 3. So it's a very small probability. So we can see these coefficients tell us basically where we can, or in which state we can expect to find our particle. Okay, so that is this problem, as I said, taken from Griffiths. I hope that you managed to follow it quite nicely. It was kind of tedious, there were a lot of integrals, but the process, as you see, is quite straightforward. So in the next video, we will finally begin with the quantum harmonic oscillator, which is a very, very important part of quantum mechanics. And it is actually a little bit tougher than this, so I'm actually quite excited to start with it. So I'll see you there.